Okay, welcome back, ladies and gentlemen. So now we're looking at B part for lesson 4.2. And when I turned off the camera, one of the people in the audience today asked me a question. They said, "Hold on, with that normal, can I write it in this form? And is it equally correct in this form?" And the answer is absolutely. Yeah, you can put it. This is called component form. This is called coefficient form because these are just the coefficients. So we'll call this, let's actually define this, coefficient form. Yes, I spelt it wrong. You guys go look up. And this would be component form. No one in the whole world makes a big deal about that, but I do sometimes. So that's coefficient form because it's just the coefficients, the numerical coefficients that are in front of the basis vectors. And this is component form because it's so many i's, subtract so many j's, plus so many k's, those are your components. So both are grand. Okay, moving on to B. Show that this normal is perpendicular to every vector in this plane. Well, that's tough. This would be easy if it said just prove that the normal is perpendicular to those two direction vectors. I just do the dot product and make sure it equals 0. But this is tough. This is asking me to prove that it's perpendicular to every vector. Well, first thing I'm going to do is I'm going to let D3 be any vector in the plane. Okay, so D3 is just any old vector in the plane. And we already have D2. Okay, so let's take a look at what we're going to do here. What I'm trying to say is if I've got a plane, and if I've got D1 here, and if I've got D2 here, they don't have to be the same magnitude. And if I arbitrarily have D3 somewhere, maybe it's here, lying in the plane, so this piece of paper, this is lying in the plane, this is lying in the plane, this is lying in the plane, I can pick up D3, I can move it, and that D3 can be composed of so many D1s plus so many D2s. And that's just simple vector addition, right? So D3, in this case, is going to be composed of TD1s plus SD2s, where T and S are elements of the real numbers. So in other words, they are a scalar. So they're multiplying it to get you that length. So let's bring that over to our proof. And so what we have here is, therefore, D3 equals T D1 plus S D2, where T and S are scalar multiples. Okay, so what that's going to give me is T2, 0, negative 1 plus S 3, 1, 0. And I'm using the reduced form of that direction vector again. And so that's going to be D3. So D3 is going to be composed of, if I do this, it'll be 2T plus 3S, that's your I, plus 1S, that's your J, negative 1T, and that's your K. So it's actually going to be 2T plus 3S, comma, S, comma, negative T. Now what I need to do is I need to show that D3 is perpendicular to the normal. Well, the normal is given by 1, negative 3, 2. So what we want to show is, we want to show that D3 cross N, not cross, dot, N is equal to 0. We're going to use the property of the dot product. So it's going to be D3, which is 2T plus 3S, S, negative T, dot, 1, negative 3, 2. We don't know what that equals yet, so we're waiting to find out. So this times this is going to be 2T plus 3S, negative 3S, negative 2T. Can you see what I'm writing? No, you can't see what I'm writing. Why is my audience not telling me that you can't see what I'm writing? You silly audience. So here's the dot product. So to do the dot product, it's this times this, plus this times this, plus this times this. So it's this plus this, which is going to give us 0. Therefore, the normal is perpendicular to D3, and D3 represents any vector in the plane R. Hey, that's brilliant. I'm so proud of myself. I didn't know how to do that when I first sat down and looked at it. I was really worried. There you go. That's cool. And I think we've explained it in a way that makes a lot of sense. This part, you just got to get over. I'm creating D3 to be any vector, and then I have to talk about that vector in terms of the two direction vectors that I had. And again, that's your diagram for that. And it could have been any diagram. Here's D1, here's D2, here's D3. They're all in the same plane. I'm going to pick it up and move it here. And notice, so many of these plus so many of these will give me D3. And that's what allows me to do this. Then the rest is easy. I know that to prove that something's perpendicular, I need to show that its dot product is 0. Kind of nice. Okay, we'll stop there and we'll start the next one.